Hello friends, I Professor Darshan Thakur from Terna Engineering College Dharashiv welcomes you on my YouTube channel for this subject head Control System Engineering. So as far as our today's session is concerned, we will try to learn the second analogous technique adopted by this control system engineering phenomena whenever it is required to convert the given mechanical system into the equivalent electrical system. So friends, we are very much aware of this thing ki in case of a mechanical system, as we know, there are three basic elements. Those are nothing but what? First one is nothing but mass denoted by m. Second one is nothing but this viscous friction, or that can be called as a damper denoted by V. And third one is nothing but what? The spring denoted by K. So in case of the previous analogous technique, whose name is nothing but what? The force voltage analogy. Already we had gone through this force voltage analogy. So after going through this force voltage analogy, we are coming on to this conclusion ki this mass is analogous to L in case of force voltage analogy. This spring is analogous to R. This K is analogous to 1 over C, and this displacement is analogous to charge. Right. In same manner, we need to realize this force current analogy technique by using this series RLC, by using this parallel RLC circuit, because these three basic electrical elements are connected in parallel form. So as these are connected in parallel form, so whenever the circuitry is being excited with certain voltage, so at that time ultimately this fundamental current or the total current will get divided in between these three branches, right? So accordingly, what we need to do, we are supposed to determine the total current flowing through this resistor, inductor and capacitor. So the fundamental current through this circuitry is given by I equals to, according to this Ohm's law, current flowing through this resistor is nothing but what? Simply it is V by R, right? So similarly, as far as these two energy storing elements are concerned, so current flowing through this inductor and the current flowing through this capacitor, we need to recall. So whenever it is excited with that certain supply voltage, so current flowing through this inductor and the current flowing through this capacitor. Current flowing through this inductor is nothing but what? It is 1 over L integral of V dt, and the current flowing through this capacitor is nothing but what? It is C into dV by dt. That we need to recall, right? So this equation will become what? The current flowing through this inductor will be 1 over L integral of V dt plus C into dV by dt, right? Then after that, as we know, according to the Faraday's law of electromagnetic induction, the induced voltage within this basic RLC element, V equals to what? The rate of change of flux per unit time, d phi by dt. Similar to your force voltage analogy, in case of force voltage analogy, this I is nothing but what? The rate of change of charge per unit time, dq by dt. Similarly, in case of this force current analogy, this voltage is nothing but what? According to this Faraday's law of electromagnetic induction, the rate of change of flux per unit time. So when we replace this V with this in this equation number 1, so this equation number 1 will become what here? Here I will rub these remaining things, and this equation can be termed as a equation number 1. So in that equation number 1, V is being replaced by the rate of change of flux per unit time. So as a result of this equation will become, here I will write this 1 over R into d phi by dt plus 1 by L followed by integral of V is nothing but what? D phi by dt into dt plus C into already we are having first order differentiation dV by dt, dV by dt, where V is nothing but what? D phi by dt. So as a result of this, it will become d square phi upon dt square, right? So the same equation will become what here? It will become 1 over R into d phi by dt. After going through this simplification, as we are having these two operators, integrator and differentiator, so the remaining term will be what? it is 1 over L into phi plus C into d square phi upon dt square. If we rewrite this equation in ascending order, so it will become what? C into d square phi upon dt square plus 1 over R into d phi by dt plus 1 over L into phi, right? So this is nothing but what? This whole term can be treated as a equation number 2, and at the same time we need to recall the basic force equation of this mechanical system. F equals to what here? Here I will write F equals to the force equilibrium equation for mass is nothing but what? M into d square x upon dt square plus the equilibrium equation for viscous friction or the damper is nothing but what? B into dx by dt plus for that spring k into x, right? When we apply Laplace transform, so it will become ms square into x of s plus bs into x of s plus k into x, right? So this is nothing but what? The basic equilibrium equation for that mechanical system, right? And as far as this equation number 2 is concerned, so this equation number 2 is nothing but what? When according to this Faraday's law, V is being replaced by rate of change of flux per unit time, the existing equation of this parallel RLC circuit will become C into d square phi upon dt square plus 1 by R into d phi by dt plus 1 over L into phi. And after that, when we apply the Laplace transform to this equation number 1, so this equation number 1 will become what? Here I will write I of s equals to the second order differentiation, so the Laplace variable will be Cs square into phi of s plus 1 over R into d phi by dt, the first order differentiation, so the Laplace variable will be s into phi of s plus 1 over L into phi of s, right? If suppose this is equation number 3, right? Then when we compare this equation number 3 with the S domain equation or the S domain equilibrium equation of that mechanical system, so we will come to know the coefficient of s square is what? M. In case of that basic equilibrium equation or the basic force equation of that mechanical system, the coefficient for this s is nothing but b, and to that k we don't have any Laplace variable. When we compare this basic equilibrium or the force equation of this mechanical system with this equation number 3, then we will try to find the different analogous term belongs to these three mechanical elements. These are nothing but what? The mass, spring and damper. As the coefficient of s square is m, the coefficient of s square is what here? C. So we will come to know this m or this mass is analogous to C in case of force current analogy, right? The coefficient of this S is nothing but what? It is 1 over R. S, the single order Laplace variable, belongs to this viscous friction or the damper. So this B is analogous to 1 over R in case of force current analogy. Third mechanical element is nothing but what? K. So here this K is analogous to 1 over L, right? Similarly, in case of force voltage analogy, this displacement is analogous to charge Q. Similarly, in case of force current analogy, this displacement is analogous to flux phi, right? Then as when we come to know this M is analogous to C, B is analogous to R and K is analogous to L. After that, what we need to do? Okay friends, so once these analogous terms are being discovered from the sake of comparison, when we compare this basic force or equilibrium equation of this mechanical system with this the derived equation of this parallel RLC circuit. So as a result of comparison, M is analogous to C, B is analogous to R, and K is analogous to L. Right. Now in that initial step, one hypothetical assumption is to be done. That is nothing but what? According to this Faraday's law, V is nothing but what? The rate of change of flux per unit time. Right. When we apply the Laplace transform to this statement, so we will come to know V of S equals to what? As we are having the first order differentiation, so V of S equals to what? When we apply the Laplace transform, so here I will write, due to lack of space, V of S equals to S times of phi of S, right? It is S times of phi of S, right? So we need to replace this whole quantity S into phi of S with this V of S, the S domain representation of that voltage according to the Faraday's law of electromagnetic induction. So whenever we are having S into phi of S, this quantity is being replaced with this V of S. So by taking into account this fact, this equation will become what here? I of S equals to what? It is Cs square times of phi of S. S into phi of S is nothing but V of S. So it will become Cs into V of S plus it is 1 over R into V of S, because this whole quantity S into phi of S is being replaced with this V of S. As far as the third term is concerned, so here we are having 1 over L into phi of S, so it will become 1 over Ls into V of S, and this is nothing but what? Equation number 4. I will put this entire term within this rectangular box, right? So this rectangular box indicates the force current analogy, where this I is analogous to force, right? Similarly, your C is analogous to mass, 1 over R, the reciprocal of resistance, is nothing but what? Analogous to your damper, right? And this 1 over L is analogous to your spring, right? So in this way, these analogous terms are to be derived from this expression by taking into account this parallel RLC circuit. So this where this force current analogy technique is being used, right? The application of this force current analogy is to, whenever it is required for we people to convert the given mechanical system into the equivalent electrical system. Most of the time in university question paper we used to have one mechanical system, and the objective is like this: draw the force voltage analogous circuit as well as the force current analogous circuit for that given mechanical system. So at that time, with the help of this analogous term, we can convert this mechanical system into electrical system, right? So this is all about this two analogous techniques: force voltage analogous technique and the force current analogous technique. So I just hope you had understand all these basic things regarding to this analogous scheme which are being adopted by this control system engineering phenomena. Thank you.